Welcome to this RF Industry Icon podcast. I'm Pat Hindle, and today I'm talking with Andrea Goldsmith, who is the IEEE Fellow. She's also Dean of Engineering and Applied Science and the Arthur LeGrand Doty Professor of Electrical and Computer Engineering at Princeton University. She's also the 2024 IEEE James H. Mulligan Jr. Education Medal recipient and recognized for educating, mentoring, and inspiring generations of students and for authoring pioneering textbooks in advanced digital communication. She also has a well-known classic textbook, Wireless Communication, which has been translated into several languages. So welcome to the podcast, Andrea.
Thank you so much. I'm honored to be here.
So I always kind of like to start off with, how you got interested in your field. So you received a PhD from University of California, Berkeley. And how did you first get interested in wireless technology?
I was very fortunate to have a great undergraduate advisor. So when I started at Berkeley, I declared engineering math because I knew I was interested in math, and I was also interested in applying it to something useful. And that was about the extent at which I knew what I wanted to do in college. And so I got an advisor who was actually an electrical engineer, Aram Tamasian, who had worked in information theory and communications. And he's the one who told me, if you're interested in math and you're interested in engineering, you should think about communications. So I started taking classes in communications, and I really enjoyed it immensely. And my first job was also in communications. That was after I got my undergraduate degree, before I went back to graduate school.
And so you did all your education there at University of California, Berkeley. Was that by choice? You thought it was the best fit?
Well, when I finished my undergraduate degree, I had no idea what I was going to do next. I certainly didn't think about going on for an advanced degree in engineering. I thought I might get an MBA or a law degree, or maybe just work. And I went to work at a small defense communications startup. This was in the mid 80s in Silicon Valley, when the Valley wasn't doing very well. And the company was an interesting organization because they only hired PhDs and people right out of undergraduate like me. And so I was working on antenna array technology, which was a precursor to MIMO technology, as well as satellite communications. And the problems I was working on were too hard for me to solve with the education that I had. And the PhDs that I was working with approached problems in really different and interesting ways that I found intriguing. And that's what made me decide to go back to graduate school, initially just for a master's. And at the time, I only applied to two universities, Stanford and Berkeley. I wasn't ready to leave the Bay Area. Stanford rejected me, so Berkeley was my only choice at that point, which I find ironic because I went on to teach at Stanford for 21 years. So I like to tell people that if you're rejected from a university, you may end up teaching there someday. But the reason I went to Berkeley was because I was admitted by the person who turned out to be my advisor, Praveen Varaya. He was very intrigued by the wireless communication that I'd worked on at the company, Maxim, as he was just starting out to build an automated highway system for California called under the PATH program sponsored by Caltrans. So he was interested in the communications background that I had. And so he admitted me, despite me not having the best grades and test scores. And it ended up being an amazing experience working with him and really solidifying my interest and passion for wireless communication.
So you mentioned Maxim Technology, and that's where you worked. What kind of design work did you do there? And, what motivated you to go back for the PhD? Was that because of the systems were too complicated for what you needed?
So in the mid 80s, when I finished my undergraduate degree, there was no commercial wireless communications. There was no Wi-Fi. There was no cellular. The cellular systems had just been rolled out in the mid 80s in Chicago. They weren't widespread yet. So I was interested in communications based on the undergraduate work that I'd done and my undergraduate advisor. And the only jobs in communications in California were in the defense industry. So I accepted the job at Maxim, and there were two different projects that I worked on. One was direction finding with antenna arrays. And so we were working on very complex mathematical algorithms, the Esprit algorithm and the music algorithm, which was based on very advanced mathematics that I didn't understand. And I remember going to the library at Stanford. This was back when we had to go to the library to look things up, and reading these very complex articles about these algorithms and the math behind them, and just really not understanding them very well. I was able to implement them, but I didn't understand them, and I wanted to understand them more. At the same time, we were working on wireless communications for the Milstar satellite system from Lockheed. And it was, how do we communicate in a nuclear war when the communication electronics gets disrupted? And I found that also to be a fascinating problem, although I was not enthusiastic to be working in the defense industry. I was much more intrigued and inspired by commercial wireless. So as the 80s rolled on, in the years that I was at Maxim, it became apparent that cellular communication was going to be a huge new commercial technology. And so I decided I wanted to go back to graduate school and study these new commercial cellular systems. This was just when the second generation cellular, which was the first digital cellular communication systems standards, were ramping up. And I was very intrigued to be part of that new wave of commercial communication technology.
And so you were also at Caltech and MemoryLink kind of at the same time. What type of work were you doing there?
When I finished my PhD, which was in 1994, I'd spent several summers at AT&T Bell Laboratories working on wireless propagation and wireless communication systems with small cells. And so I was very excited to work in wireless communication. I applied to jobs in research labs like Bell Labs, to companies like Qualcomm, which was very early days of Qualcomm, and also to academia. And I had offers at Caltech and MIT, but not in the Bay Area, which was where my husband-to-be had his startup. So I decided to take the job at Caltech. I was very excited to be in academia. And that's where I started my own independent research career in wireless communication as an academic. But I was still intrigued by industry. I was intrigued by the work that I'd done at Maxim. I was intrigued by the companies that I interviewed with when I was looking for my post-PhD job, as well as the work that I'd been doing at AT&T Bell Labs. This was just before they broke up. And so I wanted to stay engaged with industry, and I had the opportunity. I was approached by the CTO of this company, MemoryLink, to consult with them on developing a 5 gigahertz radio. So this was just after the 5 gig band had been opened up. There was not yet a standard for Wi-Fi to operate in the 5 gig band. So we developed a proprietary 5 gigahertz radio to do long distance communication. And it was very exciting and rewarding to be working on actually building a technology at the same time as doing this very theoretical research in wireless communication, which was what my work at Caltech was focused on.
And so you are a founder and CTO of a couple of startups. I think it's Quintana Communications and Plume Design. Can you tell us how you got the entrepreneurial bug and, what each company did?
Sure. So like most forks in the road in my career, I didn't anticipate them. So I didn't necessarily think I would be a startup founder. I had worked in a startup, as I mentioned, between my undergraduate and graduate work, and it was a very poorly run startup. So I knew how not to do a startup. But I also learned from that experience that many startups fail. I mean, this was the late 80s in Silicon Valley, long before the dot-com boom, and most of the startups were really struggling at the time that I was working in Silicon Valley. So it's apparent to me that if you're going to do a startup, it's likely to fail, and you've got to get a lot of things right. And that's part of the reason why I wasn't necessarily excited to do a startup, unlike a decade later in Silicon Valley when everything was booming. And if you had an idea you wrote on a napkin, you get tens of millions of dollars to go start a company. It wasn't that way in the 80s. And so I was in the university. I'd gotten tenure in the early 2000s, 2002. I finished my wireless communication book in 2005, and I had yet to take a sabbatical. So I was thinking about what I wanted to do next, and I was approached by the person who ended up being my co-founder of Quintana, Behrooz Rezvani. who said he was introduced to me by my Stanford colleague, John Chiaffi, who was the inventor of DSL. And they had worked together on different DSL standards. So I was introduced by John. And Beiruz was thinking about doing a startup around the emerging 802.11n Wi-Fi standard, which was the first standard in Wi-Fi to integrate multiple antennas. And a lot of my research had been focused on MIMO at Stanford, even going back to my early days at Maxim when I was working on antenna arrays. So I'd done a lot of theoretical work on the advantages of multiple antennas in wireless communication. And the opportunity to see if all the theory that I'd been developing as an academic, me and my students, might actually make a difference in a real technology is what inspired me to co-found Quantenna with Beiruz. He was a seasoned entrepreneur. He'd started a company around DSL prior to Quantenna that went public. So I knew I was teaming up with someone that had experience as a founder and CEO of a startup that I did not have. I thought we'd be good partners. And I was excited at the prospect of starting a company and making a big difference in Wi-Fi technology, which at the time in the early 2000s was not very reliable and not very fast. And we changed all that with Quantenna. We had the performance leading Wi-Fi chip of any Wi-Fi company for over a decade. Quantenna went public in 2016. That was an exciting day when I got to ring the bell on the NASDAQ. And then it was later bought by On Semiconductor. But throughout the decade, from the time we founded the company until it went public and beyond that, we had the very best Wi-Fi technology based in large part on the research that I had done in the university. So that was a very, very satisfying experience.
Yeah, you said most startups fail, but it looks like that was successful. And how about Plume? Was that also successful?
It was very successful too. And certainly I had no intention of starting another company, especially as quickly as I did Plume. So I was on a 2-year leave of absence at Quantenna from 2006 to 2008. I stayed engaged as an advisor and consultant to the company for another couple of years and went back full-time to Stanford without any connection to Quantenna after about 4 years. So it was about 2009, 2010, and I was ready to kind of get back into being a full-time academic. I was chair of the faculty senate at Stanford and doing a lot of other things. And the opportunity to found Plume, which initially was called Accelera Design, came along. I was approached by my co-founder at the time. And this was an idea to develop software in the cloud to manage small cell base stations in cellular systems. So this was 2010. And small cells at the time were thought to be a game changer for cellular technology because you could increase the capacity exponentially by adding small cells. They'd also use less energy and be more reliable. And yet we didn't really have a good idea of how to manage adding these small cells to macro cell, large cell systems. And the notion of putting software in the cloud to manage wireless devices in general was very new in 2010. And even though I wasn't ready to go out and do a startup again, I was still recovering from the experience at Quantenna, which was a roller coaster. With most opportunities, and especially startup opportunities, you can either say yes or no. You can't say, give me another year or two. And so I decided to take the plunge and start Plume. And we started out doing software in the cloud to manage small cells. Small cells did not materialize. They did not grow at the rate that we expected them to at the time we founded Plume. And so we pivoted to doing software in the cloud to manage Wi-Fi access points. And that's the technology of Plume. We built hardware and software. And it's very successful, even though it's still a private company. Comcast uses Plume technologies in all of their mesh networking in the home. And you can also buy standalone Plume mesh networks. And so even though it hasn't gone public yet, it's raised a lot of money. It's got a very high valuation. And it's had a lot of impact on making Wi-Fi more reliable and more secure in the home.
And so you mentioned that you moved from Caltech to Stanford. I think that was in 1999. You spent 25 years at Stanford. So can you tell us about your work there in the wireless systems laboratory, especially the stuff related to 5G and 6G that is more current now?
Sure. It was actually 21 years that I was at Stanford from 1999 to 2020. I was actually senior enough to retire from Stanford, so I'm an emerita professor at Stanford. I didn't actually fully leave. I'm just in a different role than I was before. And Stanford was an amazing place to spend the majority of my academic career. Even though I loved Caltech as well, and I was treated extremely well, it was a much smaller university, and my research has always had a strong connection to industry, and there was just a lot more industry in the Bay Area for me to connect with than there was in Pasadena and at Caltech. Plus, Stanford was a much bigger place. There were 5 or 6 faculty working in wireless communication at the time that I joined Stanford. So not only did I have a lot of people to collaborate with, but my students had a lot of faculty and other students to work with. And so it was just a tremendously energetic, entrepreneurial place. When people think about entrepreneurship, especially at Stanford, they think about it as a place where people start companies. But in fact, my view of entrepreneurship is much broader. It's where you break new ground and do new things and take risks. And that was the culture at Stanford. So it was a wonderful place to start as an assistant professor. I had amazing students, really incredible students whose ideas and brilliance and creativity and hard work is really what made my own research career, because all the work that I've done has been with my amazing PhD students and postdocs. And so being at Stanford those 21 years was a great environment to learn new things from faculty and students. It was also the heyday of wireless communication. So this is when the cellular systems had emerged as incredibly successful and growing exponentially. Wi-Fi also emerged in the 90s and grew tremendously throughout the 2000s. And so there was tremendous interest in creating wireless technology that was more reliable, more energy efficient, could support higher data rates, could support more users, could support different kinds of applications. And so the number of technical challenges for us to work on in terms of fundamental research in wireless communication, including fundamental limits, Shannon capacity of wireless, and technologies to achieve those limits, modulation, coding, multiple antenna techniques, networking techniques. There were just so many interesting problems. I felt like a kid in a candy store. More problems that I was excited about working on that I could work on, even with the amazing group of students that I had. So it was an incredibly exciting time, and Stanford was just a wonderful place to be doing that kind of research. And in addition to research in wireless communication and electrical engineering classes that I was teaching and being engaged in the department, Stanford also gave me the opportunity to explore academic leadership more broadly. I mentioned I was chair of the Faculty Senate when I went out to found Plume. Being chair of the Faculty Senate and part of the Stanford Faculty Senate for so many years exposed me to much broader issues of university leadership, faculty government, student government, how to be an effective academic leader, how to inspire faculty and students across broad sets of areas, how to do interdisciplinary research and teaching. So I learned a lot at Stanford about university leadership well beyond what I was doing in my own individual work.
Well, you had a very long, successful career there, but now I think you're at Princeton, and I heard the school is undergoing like a major expansion. They have plans to create a new neighborhood and buildings for the schools, departments, and institutes, launch interdisciplinary initiatives in bioengineering, quantum computing, robotics, smart cities, and data science. So they're significantly growing their engineering faculty there. So what made you go there? Was it this big development, or was it something else?
When I was first approached to apply for the deanship of Princeton Engineering, it was by my good friend and longtime IEEE member, Vince Poor, who was chairing the search committee for the Dean of Engineering, which was a position that he had held for 12 years. And I said to him, I'm not really a conservative leader, and Princeton seems like a conservative place, so I don't think it's a good match. I don't think I'm the right leader for Princeton, and I don't think Princeton Engineering is the right leadership opportunity for me. And he pointed me to the strategic plan for engineering that was developed when the president, Chris Eisgruber, had first come into office. So the strategic plan in 2016 called for this major expansion of engineering, in order for Princeton to have more impact, given the role of technology, not just in engineering, but across all disciplines, and the importance of technology to benefit humanity, which is Princeton's informal motto, which is to benefit humanity and all nations. There was a sense that Princeton engineering needed to grow and needed to have more impact. And so it was that spark that I read about in the 2016 strategic plan that made me think growing engineering within a great liberal arts university, within an Ivy League school where engineering has not been dominant in the Ivy League universities until now, would be a great leadership challenge and opportunity. And so after exploring, I was fortunate enough to be offered the position, and that's what motivated me to take it.
And so let's move on to, I think you've authored several books, Wireless Communications, MIMO Wireless Communications, and Principles of Cognitive Radio. Can you tell us how you picked your subjects for these books and, what motivated you to do those? Because I know there's a lot of work.
Indeed, and actually I have a fourth book that came out relatively recently on the intersection of machine learning and wireless communication, which is another really exciting topic. The first book that I wrote, I like to say I wrote the book on wireless communication because I did. That is the title of the book. And it came about because I was teaching a graduate course on wireless communication, starting at Caltech and throughout the time I was at Stanford. So for my entire career as a faculty member, starting in 1994 and until I left Stanford in 2020, I was teaching this graduate course in wireless communication. And I kept hoping that someone would write a textbook for the course that I was teaching, because it's much easier to teach a class when you have a textbook. Not only does it kind of provide a framework for students, but then you get homework problems and you can decide what to cover or not to cover that's in the textbook, but you have that option. So nobody ever wrote that book. And so every year that I was teaching the class at Caltech and then at Stanford, I would expand my course notes that I was using for the book. And in 2002, I thought that the notes had expanded to the point where I could actually write a textbook myself, because it became clear at that point that nobody was going to write the textbook that I would want to use for the class. So it took me another 3 years to finish the book. It was published in 2005. I'm still working on the second edition, so it's quite out of date at this point. But it was a labor of love. It was a huge undertaking, took a huge amount of my time. I had little kids at the time that I was writing the book, and when it was first published, I thought maybe it wasn't worth it because it took so much time away from them. But I am very proud of the book. As you mentioned at the beginning, it's been translated into multiple languages. I meet people that have studied all over the world using my book. And so I do feel like it's had a big impact on educating students and practitioners in wireless communication. So that's why I wrote the first book. And it was a single author book, and the second edition will also be single author. It's just a topic that I feel like I don't want to compromise what I want to say about wireless communication in a textbook. And if you partner with someone, whether it's in writing a book or teaching a class or creating a family, you always have to compromise a little bit in what it is that you want to do and what you want to say. The other books are co-authored books, and they're actually somewhere between a fully co-authored book and an edited book. So they're topics that were timely at the time that they were written. MIMO was the first co-authored book that I wrote after the wireless book. And MIMO was exploding as a technology. I worked on it at Quantenna. We created these amazing Wi-Fi chipsets based on MIMO. We felt like there was a need for a textbook covering all the foundational principles of MIMO communication at the time. So that was the second book that came out. Similar with cognitive radio, there was a lot of interest in using intelligence. This was before the AI craze, in radios, both as standalone radios and as networks of radios. And then the last book, again, following the same trend, AI and machine learning, even there's a lot of hype around it. It is a very powerful tool that can change the way you do physical layer communication, modulation, coding, equalization, every aspect of physical layer point-to-point communication and multi-user communication might be able to benefit from AI, not necessarily will, but might. And then networking as well. How do we do resource allocation? How do we assign bandwidth and power and data rates and reliability to different users is something that AI and ML can play a big role in. So that's why we wrote that textbook, to tap into the emerging field of using machine learning and AI in the design of wireless communications, and vice versa. How can wireless networks be used to support distributed machine learning and AI? So that was the motivation for the last book. And they've all done very well. But the first book is still my first love. And I know it's taken a long time to get the second edition out. I'm getting closer, but I will not say when it'll be done, because I've said before deadlines, which I've blown through, but it is a labor of love. And I am very much enjoying working on the second edition.
Yeah, that definitely, the first one is a classic, foundation for a lot of courses, and a lot of people have read it. I know that. So I think you have 38 patents and counting. What are some of the key ones that you developed or you're most proud of, or, that you think have a big impact?
It's interesting that as an academic, I didn't think about writing patents until I went out and founded Quantenna. I really wish I had patented adaptive modulation, which was something that came out of my master's thesis, in fact, because it's used in all wireless systems. But at the time, I didn't think to patent it, because the idea of university professors is that we advance the state of the art, we advance knowledge, and we publish it so that people can benefit from advancing knowledge. And that's still my motivation in the research that I do. And so writing patents isn't necessarily part of the DNA of university professors, or something that motivates us, or something that we're rewarded by. So why do I write patents now? Well, when I started Quantenna, I realized the value of patents. Part of our fundraising was to talk about the patents that we had. And some of the patents I'm most proud of are the ones that came out of Quantenna, particularly around dynamic digital beamforming, which was the algorithm we were using in this early generation of multiple antenna Wi-Fi to give the most reliable performance of any of the chipsets. So I realized at Quantenna that if you want to take ideas that you develop out of your research and translate them into practice, you probably need to patent them, because no investor is going to invest in a company around those technologies, whether you're the founder or somebody else's, if those ideas are not protected. And also, once you have a patent, you can license it to companies, and they're much more likely to license a patent than to try to read your papers and discern how to use these ideas in practice based on papers alone, although that does happen as well. The second company, Plume, we also developed a lot of patents. This was around using software in the cloud to manage multiple Wi-Fi access points in small cells. But in between, when I went back between Quantenna and Plume, and then after Plume, when I went back as a full-time academic, I realized that in my research, patenting the ideas that I thought might make a big difference in practice would actually facilitate translating those ideas into practice, and also could potentially create revenue for my university, which had supported that work. So that's why I now patent ideas that I think are highly relevant and potentially impactful to industry. When you ask which of my patents am I most proud of, I would probably say the Quantenna patents, because they were foundational to the technologies that we created, which were the best Wi-Fi technology in the world over a long period of time. So those were really important patents for Quantenna and for the industry as a whole.
And so you do a lot of work with the IEEE, so I thought maybe you could tell us a little bit about what are some of the key areas you're involved in there.
I love the IEEE. It's been my professional home for my entire professional career, starting in my early days as a graduate student. And I got involved in the IEEE as a graduate student. In fact, there was a big conference in San Francisco taking place, GlobeCon, in 1994. I was finishing up my thesis at the time, and they needed a local organizer. And somehow I got tapped, even though I was just a graduate student. And that's what really exposed me to the benefits of being part of the IEEE as a volunteer, not just as a student who would get at that time, you had to be a student to get the journals and magazines, and you would get a discount if you went to conferences. So that was my initial notion of the IEEE. But when I was deeply engaged in organizing GlobeCon 94, I met so many very senior people, and got a lot of leadership experience from being part of that organizing committee. I was also in that conference and other conferences able to meet luminaries in my field and talk to them over dinner or after a presentation that I made or they made. And so I found the IEEE to be just an incredible resource for me professionally on technical things and non-technical things. And so I always felt a desire to give back to the IEEE since it had given me so much. And I've played many roles as a volunteer in the IEEE. I was the president of the Information Theory Society. I was on the board of governors for the two societies I'm involved in, communications and information theory. I've been on many IEEE award committees. But the work in the IEEE that I'm most proud of is the work that I've done with many volunteers around diversity and inclusion. So this came about starting in 2016. I was at a birthday party for Tom Kylath, and Jose Mora, who is the incoming technical activities vice president, told me that he was thinking about creating an ad hoc committee to advance diversity and inclusion in technical activities in the IEEE. And he asked me if I was willing to chair this ad hoc committee. Now, given all my experience in the IEEE as an IEEE president and other things, I said, I really don't think this is going to be very successful. This is a challenging organization where making big changes takes a long time and a lot of effort. And I'm not sure the IEEE is open to really embracing diversity and inclusion. And he said, well, this is your opportunity to try. And Jose is very charming and convincing. So I said, okay, I'll do it for a year. So that started in 2016. We had an ad hoc committee with a tremendous group of volunteers, as well as IEEE staff that supported the work of the ad hoc. And something magical happened with this ad hoc committee. I mean, an ad hoc committee is 1 year, it's not permanent. And it was only within technical activities. But we invited anyone who wanted to attend our meetings to come. And we started getting people from IEEE awards showing up and people from IEEE membership showing up. So people from all across the IEEE to have an opportunity to talk about how do we enhance diversity in the IEEE? How do we ensure that diverse members in the IEEE can achieve their full potential and fully benefit from everything that the IEEE has to offer and that the profession has to offer? That committee ended up becoming a standing committee in technical activities. And then Jose became IEEE president and formed an ad hoc across the board of directors in the IEEE to enhance diversity and inclusion. And I chaired that ad hoc and then the standing committee. And it was really a group effort to bring about significant change in the IEEE around diversity and inclusion. And we did it. We changed the code of ethics and code of conduct. We created a diversity statement talking about why diversity was important for the IEEE and for the profession. We changed the culture in different units from going down to regional groups to the large cross-sectional units in the IEEE. And when I think about all of the things I've done professionally, it's one of the things I'm most proud of, that we together were able to enhance diversity in the IEEE, ensure that diverse people were included and could achieve their full potential and fully benefit from everything that the IEEE has to offer.
You definitely sound like someone who just takes on the big challenges and always succeeds. So you were the right person at the right time.
There's a lot of failures along the way. I just came from giving the welcoming remarks to the incoming engineering freshman at Princeton. And that was one of the things that I said. You look at my CV and you say, wow, you're so successful, you've accomplished all these things. But there's so many failures along the way, including my first year as an engineering student, where I almost left engineering altogether. And so you cannot be successful and have a lot of impact unless you take on big challenges. And that means you have to be willing to fail. Quantenna almost failed so many times. We almost ran out of money. We were 2 weeks away from running out of money to make payroll. Company, if the chip had come back and not worked, that would have been the end of Quantenna. So there's so many things that I failed at or almost failed at. And you learn a lot more from the failures than from the successes.
Well said. So you've won many awards, but recently were awarded the 2024 IEEE James H. Mulligan Jr. Education Medal recipient. And that was what I said in the opening. It's for educating, mentoring, and inspiring generations of students for authoring pioneering textbooks in advanced digital communications. So I was at that awards ceremony. What was it like? It was a big event.
It was an amazing event for me because mentoring and educating students is and always has been the most rewarding part of my career. I feel like I've gotten so much out of that experience. I've learned so much. I've been inspired so much by the students that I work with. To get an award for mentoring students is like being given a big piece of chocolate cake. It's like for doing something that you love to do. So of all the awards that I've won, I would say this is the most meaningful because educating and mentoring students is really paying it forward to the next generation. Every person that I've mentored and educated can then go on to mentor and educate other people. And so you have so much impact through education and mentoring, and it's so rewarding. I've learned more from my students, from freshmen to postdocs and everyone in between than I feel like I've taught them. They are lifelong friends, lifelong students, lifelong mentees. And so those relationships have really been so rewarding. And that's why this award meant the world to me. I could barely give my gratitude speech because I was so overwhelmed with gratitude to the students and postdocs that I've mentored that nominated me for this award.
Well, you have great experience in academia and in industry. So I just wanted to get your outlook on some of the future technologies. What are some of the key technologies you see coming with 6G and, what are some of the major challenges that need to be overcome?
6G is very interesting because we're not really sure how 6G should be different from 5G. And when you talk about the Gs, whether it's 2G, 3G, 4G, it's not really a new technology or system. It's kind of a marketing term. It's like, okay, how do we get people to buy new phones? Well, we'll call them 6G phones instead of 5G phones. So I think more of the evolution of cellular communication, because the Gs are really associated with cellular, as an evolution. And if you look from 1G to 2G, it was revolutionary. We went from analog to digital and all that that entails in terms of, being able to support more users, being able to support digital communications, being able to support more reliability, lower energy, lower cost, all of those things. So the 1G to 2G change was revolutionary. 2G to 3G was really about going from a small number of people being able to make voice calls to a much larger number of users being able to make voice calls. But 3G was never good at data. That wasn't what it was designed for. And so when the iPhone came out, it literally brought the 3G networks to their knees. And we needed a new type of G technology to support data, not even the data that we have today, but the data that was prevalent in the 2000s. So that really created the push for 4G technology, which is a very powerful technology. So 4G is using multiple antennas, it's using OFDMA, it's using a lot of the technologies needed to get high-speed data and fairly reliable high-speed data and a fairly large number of users. So the move from 4G to 5G was more evolutionary. We are still using OFDMA, we are still using multiple antennas. We haven't significantly changed the backbone network. There's notions of Open RAN and virtualization, but none of those have really taken off or caused dramatic changes in the way we do networking in the cellular systems. And so 6G, I think, is an open question as to what are we going to put into these networks that will be a game changer either for users or for operators, so that we can either make more money or provide better services or better applications. So when I think about, and I'll come back to Wi-Fi as well, but when I think about 6G cellular, challenges are never bet against people wanting higher data rates, right? I mean, the faster you can download data, the better. So we would like to have an order of magnitude or more higher data rates. as well as better reliability, better energy efficiency. This is at the physical layer. Now, millimeter wave was supposed to be a game changer for 5G, hasn't really panned out that way. There's technical reasons and economic reasons for that, but it's difficult to build low energy, low cost millimeter wave communications that works well in different kinds of environments and at large distances. And that will probably still be true for another decade or more. So what is going to be the physical layer game changer that's going to give us much better performance at the physical layer than we have now? Some people think AI will play a role there. I'm skeptical. I think that we really are kind of at the Shannon limit of what we can do at the physical layer in point-to-point communication. But maybe there's something else that we can't foresee, just like millimeter wave, we couldn't foresee it, and AI, we couldn't foresee that really playing a big role. There's many changes at the networking level. We're still really not even sure what the limits of wireless networking should be, or if we're anywhere close to them. So I think that there's a lot more to be done at the networking layer to support users, more users at higher data rates with more reliability than we have today. And the other thing that I think there was a hint at for 5G, but hasn't really panned out yet, is cellular networks that support different verticals. So cellular networks are built to support whatever application you want to run over it. But if you think about supporting AI, where so much computation is going to be done in the cloud, and you've got these end devices that aren't going to be able to do those computations, but may need to do some local computations. So how do we support AI in a cellular network? We don't know how to do that, and there's nothing about the network design that's optimized for AI. Same with self-driving vehicles, where latency is hugely important. You also need to have situational awareness. Again, none of this is built in inherently into networks. Telemedicine is another example. So when I think about how hardware has evolved, we went from having kind of general purpose processors, Intel processors, to application-driven processors like GPUs for doing AI. The same thing might happen within cellular networks and Wi-Fi also, where rather than having a general purpose network, we have a network that's designed to really be optimized for specific applications that are going to be the killer apps. The problem is we don't know what those killer apps are, though. So maybe we will, maybe we won't. If we don't know what they are, then we're going to have to continue to build general purpose networks that just work better. So I see a lot of opportunity with 6G. The other thing that I call the killer app for 6G is connecting the billions of people that don't have connectivity. If we think about the COVID pandemic and the divide between people that had broadband and people that didn't during the pandemic, it was enormous, much bigger than before the pandemic. And so it's clear that providing broadband connectivity to many more people that don't have it today is really important. We have that technology now. It's not a question of technology. It's a matter of cost and government will to do so, and other factors that have nothing to do with technology. So I hope that we will see in 6G networks better ways and cheaper ways and more effective ways to connect the billions of people that don't have connectivity. And then coming to Wi-Fi, which is more local, I think that it's similar to 6G. It's an all-purpose network. We haven't solved the interference problem yet. We haven't solved the ubiquitous coverage problem yet because propagation obeys the laws of physics, which can cause real problems in wireless connectivity. So there's still a huge number of exciting problems for us to solve in next generation wireless communication.
And so do you have any more thoughts on anything you're really excited about over the next, 5 to 10 years in the technical aspects that you're really looking forward to seeing?
Of course, I mean, wireless is my passion, so I'm very excited about the future of wireless. But I love technology generally. I think that's why I really enjoy being an engineering dean and an engineer. And so when I think about what are the areas of technology that have tremendous promise, the technology itself, I think bioengineering and biomedical engineering really has the potential to transform healthcare and medicine and wellness in ways we can't even imagine today. It's almost magic. When I started working in wireless. The notion that you could take a device with you anywhere in the world and communicate was like magic. We couldn't even imagine that we could do that, and now we can. When I think about bioengineering, the fact that you can take a biomedical device and cure the symptoms of Parkinson's and epilepsy and pain and incontinence by injecting an electrical signal in just the right part of the body, that's magic. And we can do that today. So what will we be able to do tomorrow and in 5 years and in 10 years with bioengineering and biomedical devices? I'm just enthralled to see how that technology is going to evolve. Robotics is another area that I'm really excited about. We've done a lot with robotics, but there's so much more to do, particularly in robotics that are interfacing with people. And I think about self-driving cars as part of that as well. It's just a mobile robot. We put my husband's aunt and uncle, who are in their 90s, into a Waymo a month ago, and they were just enthralled at the fact that you could get in the car without a driver and it would take you through the streets of San Francisco better than a taxi driver would. This is amazing that, again, if you think about the magic of what robots and flying robots and driving robots are going to be able to do for humanity, it's the future is almost unlimited. AI obviously is an exciting area. We're seeing a little bit of a burst of the bubble. I would say the irrational exuberance around AI, but it's still an incredibly powerful tool that has the potential to transform engineering, engineering design, engineering manufacturing, engineering jobs, as well as efficiencies in all businesses, in our homes, in our lives. So I'm very excited about AI. I'm happy to see the bubble burst a little bit because I think it was irrational. And now we're going to get down to how do we use this tool in really effective ways. I'm excited about blockchain. We have a center at Princeton on the decentralization of power through blockchain technology. Blockchain kind of has a bad reputation because of cryptocurrency, and there are certainly many pitfalls in cryptocurrency, but it's also something that's enabled women in Afghanistan to own businesses and do financial exchanges that they couldn't do otherwise because they're not allowed to own a bank account. So we're looking at using blockchain for distributed home ownership, distributed governance, distributed voting. So this is a technology, people call it Web 3.0. I don't know if I'd go there because it's a buzzword, but blockchain is really a very powerful technology that has many applications beyond cryptocurrency. And I'm very excited to see how that evolves, including the policy aspects, which will help prevent fraud and things collapsing around this digital technology. So to be honest, I'm excited about many technologies and also their ability to clean up our environment, to ensure our national security, to mitigate barriers to success for people that may not have the same resources as people from first world countries or from, well educated families. And so I just find technology generally magical, and what's most exciting is what we can't envision yet.
Well, thank you very much, Andrea, for talking with me today about your career, thoughts on technology, and all your work in education. We really are industry icon, and we appreciate you talking with me today.
It's been a pleasure. Really enjoyed the conversation. Thanks so much for the interview.
Great. And to our listeners, you can find more podcasts at podcast.microwavejournal.com. Thanks for listening.